Welcome to Yaka Digital Network. Today, we are looking at thermodynamics in chemical reactions. In chemistry, energy is never lost. It simply changes form. Take a lit paraffin lantern. As the fuel burns, chemical bonds rearrange, and the excess energy is released into the surrounding air as heat and light. We call this an exothermic reaction. Now, consider the chemical cold packs used at a local medical clinic to treat swelling. When you crush the pack, ammonium nitrate dissolves in water. This reaction actively pulls heat away from the patient's skin, making it feel cold. This is an endothermic reaction. To understand why a reaction heats up or cools down, think of it like a business transaction. Breaking existing chemical bonds is the cost. You always have to put energy in to pull atoms apart. Because it absorbs energy, bond breaking is strictly endothermic. Forming new, stable bonds is the profit. When atoms snap together into a new arrangement, they release energy outward. Therefore, bond forming is always exothermic. The overall temperature change you feel is just the net difference between the energy spent breaking the old bonds and the energy earned by forming the new ones. This chart shows the energy profile of an exothermic reaction. We track total energy on the vertical axis against reaction progress on the horizontal. Notice that reactants start high and products end low. The products have less energy because they released heat. This difference is the enthalpy change, delta H. Because final energy is lower, delta H is negative. Even a heat-releasing reaction needs an initial spark. This initial climb is the activation energy, the mandatory entry fee to break the first bonds. Now look at the profile for an endothermic reaction. The structure is reversed. The curve starts at a low energy baseline for the reactants and climbs to a high energy baseline for the products. The products end up with more energy because they absorbed heat from their surroundings. Since overall energy was gained, the enthalpy change here is a positive delta H. We see this upward energy climb happening constantly in agriculture. In photosynthesis, plants absorb sunlight to break down carbon dioxide and water, forming high-energy glucose. By reading these hills and valleys, chemical engineers can calculate exactly how much external power a process requires, or if a factory reaction risks overheating. Let's calculate the overall enthalpy change. The formula is simple. Delta H equals the energy required to break bonds minus the energy released from forming bonds. The cost minus the profit. Consider this scenario. A chemical reaction requires 400 kilojoules to break the initial bonds, and it releases 500 kilojoules when forming new bonds. Pause the video right now. Calculate the final delta H and use the sign of your answer to determine if this reaction is exothermic or endothermic. Taking a moment to manually solve this exact type of equation is how you secure full marks on your exams. Welcome back. Applying our formula, we subtract the 500 kilojoule profit from the 400 kilojoule cost. This gives a result of negative 100 kilojoules. Because the final number is negative, it indicates a net heat loss to the environment, proving the reaction is exothermic. Here is your summary sheet. Exothermic reactions release heat, make the environment warmer, and have a negative delta H, like burning fuel. Endothermic reactions absorb heat, make the environment colder, and have a positive delta H, like a medical cold pack. Mastering thermodynamics allows us to accurately harness chemical reactions, from cooking our food to managing medical emergencies. Thank you for watching with Yaka Digital Network. For more classes and resources, visit www.yaka.cc.